Okay. So before we deal with, some of you are like, wait a minute, like, e to the x is sine and cosine. We kind of know it's true, Euler's theorem, but let's still work with these polynomials. Let's do a little arithmetic with the polynomials. So the question is, you know, how do I deal with like e to the x squared? How do I expand that out? And you say, and the idea is, as long as you know e to the x, sine of the x, cosine of x, law, anything, you can substitute. So we know that e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. I can simply say, you know what? Wherever I see an x, I'm going to replace that with x squared. And so the idea is e to the x squared power is equal to 1 plus x squared plus x to the 4th over 2 factorial plus x to the 6th over 3 factorial plus x to the 8th over 4 factorial. Now, why do we need this? And you might be reminded that you can't find, analytically, you cannot find the integral of e to the x squared. But now you can, now you can take the integral. So once again, we can't do this analytically, but what we can do is construct an approximation at 0, and now we can do integration over it. There's some other things you have to talk about before you do this, but that's the idea. It's not part of this class, but the idea is, once again, we know how to take the integral of any terms of a polynomial, so this is really helpful. Let's try another example. How do we expand? How do we represent? How about sine of 2x? Let me move the table. Let me move my chair over. So the question is sine of 2x. Well, I know that sine. It's very basic. You're given on the formula booklet. You know that sine. Oh, it's right here. It's like all the negatives. So we know that sine is like negative something over 1 factorial minus something cubed over 3 factorial plus something to the 5th power over 5 factorial minus something to the 7th over 7 factorial. And so the idea is, for sine, you would have just put the x's in. But now, because it's 2x, you put the 2x's in there. And what we've done, we've expanded out sine of 2x as a polynomial. So the Maclaurin series is 2x plus, minus 8x cubed over 6 plus 32x to the 5th over 120 minus 128 x to the 7th over 7 factorial. 120 times 70 is 840. Obviously, you have a calculator, but this is the idea. So this is sine of 2x as a Maclaurin series. Last example I want to work on is x cosine of 3x. So the question, how do we expand this out? Do I have to expand x? How do I do this? Well, it's simply, you're just multiplying x times cosine of 3x. So we know that cosine of 3x as a Maclaurin series is 1 minus 3x squared over 2 factorial plus 3 to the x to the 4th, 4 factorial minus 3 to the x to the 6th over 6 factorial, and so on. And then all you do is just multiply an x through. That's it. So you have x minus, what do we have? It's 9 over 2 x to the 3rd plus, well, let's see, 81 over 24 x to the 5th minus, what's 3 to the 6th power? Let's see, hey Siri, what is 3 to the 6th power?
3 raised to the 6th power is 729.
729 divided by 720 x to the 7th, because the x has to multiply through. And this is the Maclaurin expansion for x cosine 3x. Why do we use it? I think computers like it better. I think it's useful for computations when computers want to evaluate a any type of function. If we can make it a polynomial, it's just easier for the computers. I'm guessing. Let's move on. So let's get back to so now that we know that we can substitute, let's get in here for a second. This is kind of cool. You'll like this. Ready? I mean, this is basically the end of the course. Like, this is the end of calculus. This is how I usually ended the course. So, number 5, yeah. So, what I want to do is, you'll like this, actually. What I want to do is I want to manipulate e to the x, because I can. So, I know that, so here's the proof of Euler's theorem of, the connection of exponentials and trigonometric. So I want to put e to the ix. That's no big deal. I just replace x with I to the x. So that's equal to 1 plus ix squared over 2 factorial plus ix cubed over 3 factorial plus ix to the 4th over 4 factorial. Let's go to the 5th power because we're having a good day, right? So we have this expansion. Well, let's pretty this up a little bit because we have to take care of some things, right? So we have 1 plus ix. Well, I squared is negative 1, so this is minus x squared over 2 factorial. What's going on over here? Well, I cubed is negative I. So this is minus I x cubed over 3 factorial. I to the 4th is 1. So we have plus x to the 4th over 4 factorial. What's going on over here? I to the 5th is I. I to the 5th is I, right? Let's see, 0, I squared, 3rd, 4th, 5th. So this is plus I x to the 5th over 5 factorial. Let's do one more term. And so I to the 6th power is negative 1, right? Because, 0, I to the 1st, I to the 2nd, I to the 3rd, I to the 4th, I to the 5th, I to the 6th, negative 1. So this is minus I to the 6th over 6 factorial. And so you say to yourself, okay, let's organize this a little bit. So I want, maybe you're back to complex numbers and you say, okay, real parts, imaginary parts. So you're like, fine, this is real, this is real, this is real, I just said this is real, and then this is, the other part is maybe this is imaginary, this is imaginary, this is imaginary, and then you organize it together, and you're like, wait a minute, this was cosine. And then you say, hey, Mr. Adler, wait a minute, this is I times sine. And so you got this idea, this is the proof that e to the ix is equal to cosine of x plus I sine of x. So we are able to prove this. You're given this. This is our proof. And then finally, if we let x equal pi, we have e to the pi, which is equal to cosine of pi plus I sine of pi. Well, we know sine of pi is 0. We know cosine of 180 is negative 1, and we get e to the I pi equals negative 1. And that is how we prove, this Euler's equation, that e to the pi I is equal to -1. Good.